Today we are going to learn about the concept of electrons and holes and the mass action law in semiconductor. Let's start with the difference. So in the previous video we have learned about the overview of intrinsic semiconductor and extrinsic semiconductor. In this we are going to learn about the difference. We distinguish them by considering various factors like doping, addition of impurity, density of electrons and holes in semiconductor material. Intrinsic semiconductor. So what is intrinsic semiconductor? It is a pure form of semiconductor. इसमें कोई additional impurity नहीं रहती है. Example silicon and germanium. On the other hand, when we add pentavalent impurity or trivalent impurity like arsenic, aluminium, phosphorus, gallium, antimony is added, so it become extrinsic semiconductor. Extrinsic semiconductor are of two types: pentavalent, element of fifth group in periodic table, and trivalent, they are third group element, and इनमें 3 electrons होते हैं outermost orbit में. In intrinsic semiconductor, addition of impurity doesn't take place, where in extrinsic semiconductor we add some impurity and the process of adding impurity is called doping. Density of electrons and holes in intrinsic semiconductor is same. इसमें नंबर ऑफ फ्री इलेक्ट्रॉन इन कंडक्शन बैंड इक्वल होते हैं नंबर ऑफ होल्स इन वैलेंस बैंड के. इन केस ऑफ extrinsic semiconductor, number of holes are not equal in p type, and holes are in p type, holes are majority carrier. In n type, electrons are majority carrier. Now the electrical conductivity. intrinsic semiconductor की लो होती है, whereas in extrinsic semiconductor electrical conductivity is high. Impurity like arsenic, antimony, phosphorus, aluminium is added to silicon and germanium to form an extrinsic semiconductor. और silicon and germanium के pure crystal use होते हैं intrinsic semiconductor में. intrinsic semiconductor में electrical conductivity function होती है temperature की. in extrinsic semiconductor, in extrinsic इलेक्ट्रिकल कंडक्टिविटी डिपेंड करती है अमाउंट ऑफ इम्प्योरिटी और डोपिंग पे. नाउ द इलेक्ट्रॉन्स एंड होल्स इन सेमीकंडक्टर. टू अंडरस्टैंड द कॉन्सेप्ट ऑफ इलेक्ट्रॉन्स एंड होल वी नीड टू अंडरस्टैंड द कॉन्सेप्ट ऑफ इलेक्ट्रॉन. इलेक्ट्रॉन एटम के नेगेटिव चार्ज पार्टिकल्स होते हैं and together they create negative charge to balance the positive protons, which are the positive charge in nucleus. They are extremely small in size, 1000 times smaller than mass of proton. So germanium form covalent bond with another germanium atom. In this diagram you can see the germanium form covalent bond with the another germanium atom. 4 electron in its outermost orbit called valence electrons, and when they receive some external energy, one electron moves out in the lattice and gets free. जब ये external energy receive करते हैं तो जो इलेक्ट्रॉन होता है, एक इलेक्ट्रॉन वो क्रिस्टल से बाहर आ जाता है और वो 1 इलेक्ट्रॉन बाहर आ जाता है लेटिस स्ट्रक्चर में और वो फ्री हो जाता है और वो होल क्रिएट करता है. and the hole is created and the electron from neighboring atom occupy the place of hole and again create a hole at another space. फिर से neighboring atom का इलेक्ट्रॉन ऑक्यूपाई करता है होल की प्लेस और अनदर होल क्रिएट करता है और ये प्रोसेस रिपीट होती है. And the importance of hole is that it serve as a carrier in the same manner as electron. Now you can see when we apply external energy, electron gets free and which create a hole, and the electron in another atom which also gets free and create another hole. This process gets repeated. Now coming to the mass action law. Mass action law in semiconductor. In semiconductor, law of mass action is relation between concentration of free electrons and holes. under thermal equilibrium. So in intrinsic semiconductor, we add pentavalent impurity, which is n-type. So number of electron present in conduction band will increase, or number of holes in valence band get decreased. If we do p-type of impurity, which is trivalent, so number of holes in valence band increase and the number of electron in conduction band decrease. Then the rate of recombination increase due to presence of large number of electrons in hole due to doping. हमें कुछ टर्म्स याद रखनी है विच आर एनर्जी गैप. सिलिकॉन का 1.1 इलेक्ट्रॉन वोल्ट होता है, जर्मेनियम का 0.7 इलेक्ट्रॉन वोल्ट होता है. इलेक्ट्रॉन मोबिलिटी ऑफ सिलिकॉन इज 0.135 मीटर स्क्वायर पर वोल्ट सेकेंड. इट इज़ डिनोटेड बाय म्यू, एंड फॉर जर्मेनियम इट इज़ 0.39 मीटर स्क्वायर per volt second. Hole mobility for silicon is 0.048 meter square per volt second, and for germanium it is 0.19 meter square per volt second. Here one important term, intrinsic carrier density for silicon, it is 1.5 into 10 raised to the power 16, and for germanium it is 2.4 into 10 raised to the power 19, and the density of silicon is 2.33 into 10 to the power 6 gram per meter cube, and for germanium it is 3.32 into 10 to the power 6 gram per meter cube. Here statement is under thermal equilibrium, product of free electron concentration N and the free hole concentration P is equals to constant square of intrinsic carrier concentration, which is Ni. So here you can see the product of, here you can see free electron and free hole का concentration, free electron and free hole concentration का product intrinsic carrier concentration के square के equal होता है under the thermal equilibrium. So therefore N dot P is equals to Ni square, which is product of free electron concentration and free hole concentration, and Ni is intrinsic carrier concentration. So proof. Now coming to the proof. Because of thermal energy की वजह से generation of charge carrier, which is capital G, and recombination of charge carrier, which is denoted by capital R, under thermal equilibrium. Thermal equilibrium में capital G is equals to capital R. Now the capital R is directly proportional to P, which is concentration of holes, and capital R is directly proportional to N, which is concentration of electrons. So the capital R is directly proportional to product of free electrons and hole, which is Np. Capital R, so therefore capital R is directly proportional to Np, and so now the R is equals to, capital R is equals to small r Np. R is proportionality constant, and in intrinsic semiconductor G is equals to R Ni square, which is intrinsic carrier concentration. Ni square is intrinsic carrier concentration. Therefore capital G is equals to capital R, but in the thermal equilibrium capital G is equals to capital R. So now now putting the value of capital G and capital R. So value of capital G is R Ni square, which is intrinsic carrier concentration, is equals to R Np, which is the value of capital which is the value of capital R, which is R Np, which is product of free electrons and product of free electrons and holes, and so Ni square is equals to Np. Therefore hence the Ni square is equals to Np, hence proof. So we prove the product of concentration of free electrons and the concentration of holes is equals to square of intrinsic carrier concentration. I hope you guys understand.